Hello APC Mechanics students, today we'll solve the past paper of RQ 2009 exercise 1. A block of mass m over 2 rests on a frictionless horizontal table, so always remember that the figure appears above the text. As shown above, it is connected to one end of a string that passes over a massless pulley and has another block of mass m over 2 hanging from its other end. The apparatus is released from rest, which means the initial speed is 0. And because the pulley is massless, which means that the tension is transmitted equally at both ends. They want in part A to derive an expression for the speed Vh of the hanging block as a function of the distance d it descends. We know this is possible whenever we have access to the acceleration A of the system. And for such type of configurations modified Atwood machine, we know that the acceleration would be, so it's a fractional mass multiplied by g. In the numerator would have m over 2, and in the denominator would have the total mass, which is given by m over 2 plus m over 2. Then basically all the masses cancel due to the cancellation effect. That would be half divided by 1 multiplied by g, which is half g. And we know it's released from rest, so we can use that v is the radical, or let me say like that, plus 2ax delta x, and that would be v is given by the double of the acceleration, which is g over 2 multiplied by the distance d. Now let's do all the steps carefully because they told us derive, and in a free response we need to provide all the explanation. Then we need to apply Newton's second law simultaneously for the hanging block and for the block that rests on the table. So let me start by saying apply Newton's second law. And here it is more important to mention for which body we're applying Newton's second law. Let me start by the hanging block. And it's given by F naught is ma. Now what are the different forces acting on the hanging block? We have the pull of gravity plus the tension force, which is equal to m over 2 multiplied by a. And now we can say projection along the vertical Now the positive direction is taken to be down because it's accelerating down, so that would be m over 2g minus the tension is equal to m over 2 multiplied by a, and in this case the tension is expressed as m over 2 multiplied by g minus m over 2 multiplied by a. Now in order to determine the acceleration, we need again to apply Newton's second law for the block on the table, and we need to project. So let's again say apply Newton's second law for the table on the block, for the block on the table. And that would be F naught is given by ma. What are the different forces acting here? The table is frictionless, we don't have friction, we have the pull of gravity down, normal push up, and the same tension along the string toward the right. Then that would be the pull of gravity plus the normal push plus the tension is given by m over 2 multiplied by a. And now we will do projection along the horizontal. So the pull of gravity, its projection would be 0 as well. So for the normal push, the tension would be positive because it's the one which is providing acceleration. Then Ft is given by m2 over a. Now we will equate both tensions. So the tension would be equal to the tension, which means m over 2a is equal to m over 2g minus m over 2a, and we're interested in determining the acceleration. Now moving this to the left hand side and factoring out a, that would be m over 2 plus m over 2 is given by m over 2g, which means the acceleration indeed is given by fractional mass m over 2 divided by m over 2 plus m over 2 multiplied by g, and doing the same calculation that I have explained previously, that would be half g. But yet I didn't find the final velocity, so let me squeeze this font, this typing, sorry. So let me try to do it here in this small space. Now we know that v square x is equal to v square x0 plus 2ax delta x. Now the initial speed is 0, the acceleration now is g over 2, and delta x is basically d. Then v, the final speed, would be given by 2 multiplied by g over 2 multiplied by d, making the final speed to be the radical of gd. So this is basically vh. Okay. Now the block and pulley system is replaced by a uniform rope of length L and mass m. What does it uniform means is that the mass distribution is the same, with one end of the rope hanging slightly over the edge of the frictionless table. The rope is released from mass, and at some later time there is a length y of the rope hanging over the edge as shown below. Express your answers to parts B, C, and D in terms of y, L, m, and fundamental constants. In part B, they're telling us to determine an expression for the force of gravity on the hanging part of the rope as function of y. So we know that the pull of gravity is given by the mass times g. Now the thing is that we need to find the mass associated with this length in order to determine the pull of gravity. And this is related to mass distribution. Now total mass m corresponds for this length L. So we can say that m over L is equal to the small mass m divided by y. What does this mean? This ratio, which represents the mass distribution, is equal to the mass m of the hanging rope associated with this length y, and we're interested in determining m. So m in this case is given by m divided by capital L multiplied by y, and indeed in this case the pull of gravity is given by mg, which is also given by m divided by L multiplied by y multiplied by g. And we have expressed our answers in terms of y, L, m, and fundamental constants. In part C, we need to derive an expression for the work done by gravity as function of y, assuming that y is initially 0. Now we know that the work done by force is given by the line integral of the force. Let me write it like that, then I will explain. From initial position to final position. Now here, you should be very careful when performing this integral, because you need to identify what's your initial position, what's your final position, what's the direction of the force with respect to the default positive y direction. But if you think about it, the rope is going down, the hanging part, and we know that whenever something is descending, the work done by gravity is positive. So now we can ignore this dot product and the initial and the final position. We will be integrating from 0 length to the final length y, assuming that y is initially 0. For this reason the lower bound is 0, and the final length would be y as function of y. And we know that the pull of gravity in this case is given by m over Ly g dy. So why we have ignored all the positive and the negative signs? Because we know that our work done by gravity while going down would be positive. Now m, l, and g are constants, can be dragged out. And we're left with the following integral. A linear integral would give us a quadratic. Then in this case, the work done by gravity would be given by m over l to lg multiplied by y square. Now before proceeding to the other part, so whenever we're talking about work done by force, this can be related, since the first part A, we have found speed, and here we have replaced our system by rope. So it seems that we're gonna relate this work to speed, and this can be done by the work energy theorem. And indeed they're asking us in part D, derive an expression for the speed Vt of the rope as a function of y. So here we can apply the work energy theorem. Then let me say, apply work energy theorem which means the variation in the kinetic energy representing the energy injected or extracted is equal to the work done by all the external forces. Now kinetic energy final minus kinetic energy initial would be equal to the work done by all the forces. So what are, here you should pay attention. Now the work done by all the forces, we have two gravitational forces, one which is acting on the hanging part, and another one which is acting on the part which is on the table. And we have the work done by the normal push. I won't include the work done by friction because this is frictionless. So here pay attention. I will say the work done by gravity for the hanging part, which is this one, plus the work, I will say work G prime for the part that is resting on the table, plus the work done by the normal push, because this includes all our system. And moreover, why? Because the energy is being injected, it's not only injected for the hanging part, but also for the part which is moving on the table, because we have injected speed partly here and partly here. Now the work done by this force is 0 and the work done by this force is 0. Why? Because the displacement of the part of the rope which is on the table, it's being displaced to the right, and the forces are acting vertically, so they produce no work. Now our initial kinetic energy is 0, and our final kinetic energy is being represented by half mass times the speed to the power of 2. And what is the mass of the system? This is the total mass, which is m. So here I will write half total mass m multiplied by Vt to the power of 2. That would be equated by mg divided by 2l multiplied by y square. Now m with m would cancel, and half with half would cancel. Then Vt would be given by the square root of g divided by l multiplied by y square. So basically, what does this expression gives us? It is as function of y. Whenever we know the value of y, we can determine the final speed of the hanging part. Now in part E, the hanging block and the right end of the rope are each allowed to fall a distance y, the length of the rope. The string is long enough that the sliding block does not hit the pulley. Indicate whether Vh from part A or Vt from part D is greater after the block and the end of the rope have traveled this distance. So is Vh greater or Vt greater, or the speeds are equal? I would go for equal, and let me justify why. In part A, the speed was given by radical GD. Now here, our speed is given as function of y. So it cannot be a constant unless we determine what is the fallen distance y by the rope. And they're telling us are each allowed to fall a distance y. So let's replace Vt y for L in Vt. So Vt, which is function of y, If we replace the value of L, that would be given by the square root G over L multiplied by L square, and that would be given the radical of GL. And here, if the falling distance is L, then D would be replaced with L as well. So we will say that VH is given by the square root of G multiplied by L, which is equal, so both speeds are equal. Then both speeds are equal. Then that's it for me in this video, guys. See you soon in a new one.